Okay, so before we step into this function, we're going to analyze the image a little more. So we're going to go into our Colab environment and we're going to open our detect notebook. If you haven't set up your Colab environment, you'll have to do that first. You'll see a link to that video here. Otherwise, if you have already done that, let's jump here to reading and analyzing the image, and let's open that. So as usual, the first thing that we're going to do is mount our drive and connect to Google Drive, and then OK, continue, and so forth until this has been loaded. Okay, so the first thing that we're going to do is import OpenCV. OpenCV is the world's biggest computer vision library, and it has over 2,500 algorithms. It is an ideal library for image processing, and it has most of the traditional computer vision algorithms, as well as some of the newer ones as well. And if you're not familiar with it and you would like to know more, there are a number of free tutorials online that you can follow. So let's jump back to our Colab. Here, we're just going to import the library. And here, we're just saving the path of the image that we're going to load, which you can see also, YOLOv5, data, images, and that's our image. Okay, so let's import that. And now here, the first thing that I'm going to show you is that if we use OpenCV IMShow function, we would actually get an error here in our Colab environment. And this is because IMShow is disabled in Colab. So in order to be able to show our image using OpenCV, what we'll actually have to do is import this function, cv2_IMShow, and then we'll be able to display it on our Colab. So I'm going to comment this since we're not going to use this in the future. I just wanted to show you that. And then here, we're doing that import, and we're feeding the path for that image. We're using cv2.imread, and we're using this function so we can actually display it here. And this is the image that we're going to be using for our YOLOv5 prediction. Now, before I move on, let me talk a little bit about the channels. So the image path that we have is in RGB, that is red, green, and blue channels in that order. And actually, most of what I would call the outside world works in RGB format. When the OpenCV library was created, the default channel handling was BGR. So the OpenCV library is built on this premise, and its associated functions use the BGR format. So when working with OpenCV, we'll often work in BGR format, but when we want to display things, we will show them in RGB so that the colors are properly mapped. Now, very important, cv2IMShow expects the input image in BGR format, as we're providing, in order to display it in RGB format. So this is very important to get the right displays. And that's why I'm showing here at the beginning the format that we're using so that we don't get confused. RGB, our input image, and then BGR is what IMRead stores it in. Basically, it inverts the channels, and then BGR image to show it as an RGB. I know this is a little confusing, that's why I'm explaining it, but it's important to know it in order to effectively use the OpenCV library. All right, let's continue now. So for that same reason, our BGR image, we could convert it to RGB. However, given that IMShow expects the image in BGR format, the channel interpretation will be inverted and we will get the wrong image. Let me show you. Again, this function is fine, but IMShow expects a BGR image, and we provided an RGB image. So it thought B was R and R was B, and we got this funky image. So we just have to be careful. Now, we could do another thing. If we want to show in BGR, well, we could. This is rather silly, but I'll just show you that it works. Our BGR image has been converted to RGB, and this is an RGB image. Again, we cannot display it as RGB with IMShow because we'll get a funky image, but we could convert our RGB image to a BGR image here, which is basically the same that we had right here. We had our BGR image. But here we've done this double conversion, which again is very silly, but it proves that this works. When I run this, we'll still be getting our BGR image that you can see here, but now we'll also get our RGB image because we're feeding a BGR image. I know this is confusing, but that's why I'm trying to, hopefully I'm not creating more confusion, but this is important to know. Our BGR image, as well as our RGB image with this double conversion. We can also use the IMWrite function if we want to save something to disk, or in our case to our Google Drive. So you can see we have data images and we have our image. If I run this, we'll create an identical image. Again, we need to provide the input in BGR because OpenCV works in the BGR format. So if I just run this, it returns a Boolean confirming that the operation has been performed successfully. And then if I go here, automatically showed here. The image size is slightly different, and that might be related to the reading and writing algorithm, but these are identical images. If I toggle from one image to the other, you can see that they're the same. We can delete it since this was for demo purposes. We can also perform other operations on that image. We can print the type to the terminal. So we're working with an NumPy array, and NumPy is the fundamental package for scientific computing with Python. So an array is to NumPy what a tensor is to PyTorch. And NumPy.array is the most fundamental object of the NumPy library. In our case, we'll show the values of the pixels within the image. Now we can also print the shape. Important to note that the image shape is in the height, width, and channels order. Our image has a height of 768, a width of 1024, and 3 channels. We can also print the values here. Now, I'd like us to analyze the image a little closer, but before we do that, I'd like to show you another way of displaying an image here on our Colab that uses the Matplotlib library, which is one of the most common tools for visualizing data within Python. And here we're calling the IamShow method of this library. Here, Matplotlib expects the image not in BGR as OpenCV does, but in RGB. We're actually using here the RGB that was converted right here to be able to input that into Matplotlib and get the correct results. So let's run that. So 768 height, 1024 width. So in order to cross-reference the results that we have here with VS Code, let's run this cell. And let me scroll here just enough to see everything. So again, our image dimensions are height, width, and channels. So if we want to be able to display the first column, we want the height, but we want the first index on the width, and that's why we're showing here 0. So we want all the height and the first index of the width, and we want the 3 channels. So when we print that, we get these values here, which correspond to this vertical of the pixel values. So if we look at the first 3 pixels and we cross-reference that with VS Code, we can see here in IM0 that we have values 153614, 0190, and 416442, which corresponds to the same values here. And similarly, if we want to display the first row, meaning this row right here, well, in that case, we'll need the whole width, and that's why we have the column. And we'll need the first index of the height. So the height, we need the first index, and that will give us the first row from left to right, which is here, and also in our VS Code. If I open the first index for the width, we get 153614, 7286, 184118, which again corresponds to the 3 values that we have here of these 3 pixels. Now let's keep going. Now, it is difficult to see how different pixels have different values when you look at a large image. But if you look at a patch of the image, let's say a 17 by 17 patch, then it is easier to actually see the differences one pixel to the next. So let's run this. You can see that this is extremely small, but if we display with Matplotlib, this is much better. And we can actually see these 17 pixels from 0 to 16, how they're different from each other. And this corresponds to a 17 by 17 patch, starting from the top left of the image, from the 0, 0 coordinate. You can also see it here. The X value of the pixel is horizontal, left to right, and the Y value of the pixel is vertical, top, bottom. So the pixel 0, 0 is this one. And also the coordinate of that pixel, the 0, 0, is often the top left as well, even though this is the whole pixel. And then pixel 4, well, 1, 2, 3, 4, 7, vertically, would be this one. Now we can also show the different channels. We can actually display the channels independently. So given that this is BGR, first channel or index 0, index 1 and 2 will show each of the channels independently. So let's run this. Okay, so let me scroll and let me show this from the top. So here we're showing the blue channel, which shows colors with a high component of blue, brighter, where the value for each pixel can range between 0, pitch black, or 255, completely white. So this pixel with X and Y 640 and 30 respectively. So somewhere right here where we see the sky, we can see that the blue component is predominant, as well as the green actually, and a little less of the red. We can also visualize this in a color palette. Again, be careful, this is in RGB and we're using BGR. So we'll have to put first value here, 52, 226, and 189. And the result is the color of the sky of that part of the image. Similarly with the green, you can see that the green component of the image, such as the leaves, are brighter. And with red, is brighter because the red component is pretty high.